BC Calc students, here we go. All right, BC Calc students, Mr. Gennard here. It's great to see you. I want to get going on a lesson that I have prepared here for you. Areas and the definite integral. This is the real deal with the calculus. We're going to be undoing the process of differentiation from now on, and there's lots of tricks to it, and there's all kinds of excitement involved here. And so here we go. Let's start. I just showed you this briefly last week, but here we go. So areas and the definite integral. So the purpose of today's lesson is to make the jump from Riemann sums to what's called the definite integral. Say it, definite integral. You sound smart when you say it, all right? As you know, the Riemann sums we've been using have only approximated the area under a curve. And today we're going to aim for the exact area under a curve. And before we start, you should just know that there are some integrals that can't be calculated algebraically. There is no number, there's no finite number of, add, subtract, multiply, divide, and extraction of roots, like the 5th root of this, the 17th root of that. There are some integrals that you simply can't integrate. And I don't mean you don't have the ability to, I mean mathematically it's impossible. And so it makes calculus interesting. There's lots of ways of handling integrals. There are a lot of techniques to handle integrals. On your BC test, you can be assured every single integral they give you. Well, actually, that's not true. Sometimes they might give you one that can't be integrated, but they won't ask you to integrate it. They'll give you questions that feel like you have to integrate it, but actually you just have to use the information provided and you don't actually need to calculate the integral. Okay, so anyhow, here we go. Suppose we want this exact area here. Okay, this function is f of x is x squared plus 4 on the interval from 0 to 5 as pictured below. And suppose we decide to do a right Riemann sum with 5 subintervals. So what we're going to do is we're going to estimate it first, and then we're going to actually calculate it exactly. We'll see how our estimate compares. So if we do a right sum, we're going to break this into 5 intervals. So each rectangle, we draw a vertical line, and then we're going to use the right edge, like so. Okay? So first rectangle, second rectangle, we're calling this area 1. We're calling this area 2. This one we're calling area 3. This one we're calling area 4. That entire one. And then this is area 5. Whoops, area 5. Okay, and so the total area here. Oops, I didn't do that right. Oh, I'm sorry. Wait a minute. We're doing the right Riemann sum. Okay, a right Riemann sum. So we're picking the right edge of the interval. Okay, Riemann sums don't require that these be the same distance, and it doesn't say you have to pick any particular point along here unless it tells you to use a right Riemann sum with 5 subintervals of equal width. Okay, so you're certainly welcome to make these intervals of equal width, but you do not have to, and you don't have to pick the right side unless it tells you to. In this case, it did. Okay. But if we're doing a right sum, the area of the first rectangle is the height times the width. Well, the height of it, you'd evaluate it at 1 on which is the right side. You put a 1 in here. 1 squared plus 4 would be 5. 1 squared plus 4 is 5. 5 times 1 is 1. Okay. Area 2, we put in the right side 2. That would be 2 squared plus 4, which is 8 times 1, or 8. Area 3 would be, we put in a 3 squared plus 4 times the width. So what is that? 9 plus 4, 13. Okay, area 4, we'd put in a 4 for this side. 4 squared plus 4. That's times 1 equals 20 times 1, which is 20. And then finally, the last rectangle, 5 squared plus 4 times 1, which is 29. Okay, and just to check my work here, because this is a quadratic function, these should have a consistent pattern. This goes up by 3, this goes up by 5, this goes up by 7, and this goes up by 9. And quadratics will do that. This goes up by 2, this goes up by 2, this goes up by 2. And so you'll notice the second set of differences is a constant. That tells you it's a quadratic function, and sure enough it is. So I know I did my calculations correctly there. So we need to add all of these up. So basically the area of this is 5 plus 8 plus 13 plus 20 plus 29. Okay, and this is clearly an overestimate of the area because this function is increasing, and we're using these flat edge tops. And so there's all this extra area we're accounting for that really isn't even there. 5 plus 8 plus 13 plus 20 plus 29. 5 plus 8 plus 13 plus 20 plus 29, 75 square units. And that's definitely an overestimate. Okay. If we use summation notation, we might write that the area is the summation from n equals 1 to 5 of, okay, when it was 1, we put a 1 in here, n squared plus 4, and then times the width. Okay, and there we have it. Okay. All right, and in more general terms, this is generally how Riemann sums are written. Okay, I didn't invent the notation. This looks a little hinky in here. I didn't decide to do that. Straight out of your textbook. This says the sum of n rectangles is the summation where k equals 1 to n of, this is the height of each one of those rectangles. You're evaluating this function at a particular point. C sub 1, in this case, is 1 because we evaluated at the edge, but C sub 1 could technically be anywhere. I don't want to label the width of it as C sub 1, but C sub 1 is any one particular value in here. We could evaluate the height of this at any value we want in here, okay? So notice that the segment tells us to repeatedly add up. C sub k tells us where to evaluate the height of rectangle k. So C sub 1 is, well, where do you want to evaluate the height of this one? For us, it was at the right edge, but you don't have to do that with the Riemann sum. We could have chosen any point in here that we wanted, and that would be an acceptable value for this. And then f of C sub k is the height of rectangle k, and this is the width of rectangle k, and it's not always the same. For us, it was. We chose to make them equal, but on your BC Calc test, you won't always make those equal widths. And there's examples in the homework and such where you don't make them equal width for a Riemann sum. And so we'll definitely get into that. Okay, so this brings up a key definition, the definite integral as a limit of a Riemann sum. So if we have a function defined on a closed interval from a to b, for any partition P, so any way we choose to slice this vertically into rectangles, if the limit as the norm approaches 0, so the widest interval, as long as the widest interval approaches 0, okay? If the widest one approaches 0, all the other ones have to approach 0 as well, okay? Extremely important that the widest ones approach 0. Okay, then when we add up all of those areas, we in fact will get an equal sign here. We will in fact get a finite number I, regardless of where we choose C sub k in each subinterval. It wouldn't matter if it's left, right, center, or some random point within each rectangle. Okay, if that's true, if we do in fact get a finite number, then we say that this function is integrable, meaning the opposite of differentiable, and that number that we get there, I, is the definite integral of f over the closed interval from a to b. And page 276 has more details about this. So if we want to express the exact area, we go from here to this new notation where we say this is equal to the integral. So this integral has a procedure associated with it, which I'll go through with you. So this says we're going to go from a lower limit to the upper limit. We're going to add up an infinite number of rectangles. This is the height, and that's the width. Okay, and what's cool about this, the height is just, you just evaluate this at every single value of x between a and b. And what's cool is this width is infinitesimally small. And so what's happening here is you're adding up an infinite number of rectangles, each of which has an infinitesimally small width, which is kind of weird. And if you do that, you end up with, if the function is integrable, you end up with a finite number, which is really cool. That's what's going on here. Okay, the right side of the equation is called the integral of f from a to b. A is the lower limit or the lower bound of integration. B is the upper limit or upper bound of integration. That's kind of cool because that's the low and that's the high, right? And this double candy cane thing is the integral sign. Actually, that's where the candy cane came from. A candy maker wanted to make his daughter a special type of candy for Christmas one year. I think it was in Germany, and was not able to get the candy cane to hang. The problem was that candy, that's a hard candy. It has to sort of cool. And when it cools, it hardens. And the problem is he just couldn't get it to be in a natural shape. Gravity kept pulling it down. And so he was only able to make half of a candy cane. And so that's why we have the candy cane shape. When you have a candy cane, you actually are eating half of an integral sign. That really is a true story. Okay, the function f of x is called the integrand. So the integrand is just this piece here. It's the thing being integrated. It indicates the height of each infinitesimally small rectangle at every single value of x. And dx represents the width of every infinitesimally small rectangle. And it also indicates the variable of integration. We often call this the dummy variable because you could put any variable in here you want. You could do f of y dy, f of z dz, f of w dw. So this is off that variable itself, x, is often called the dummy variable. Oh, here we are. X is called the dummy variable because as long as the variable f of x matches dx, you would always get the same answer. So this integral is identical to this, is identical to this, is identical to this. So it doesn't matter what variable you put here and here as long as they match. That's the key thing, they have to match. If you said f of y dx, that would be a problem, okay, because they don't match. All right? Okay, I will catch you at the next video, folks. Okay, see you then. All right, bye-bye.